Hey YouTube, this is my first video in my module on solving systems of equations, and we're going to look right off the bat at an application situation in which we would use a system to solve. So a few things I want to say as we go through this is kind of recommendations to solve an application problem as well as how you solve a system in the first place. So it says a total of $25,000 is invested in two funds, okay? Two funds paying 7% and 4% annually, okay? Simple interest. So I'm going to underline any portion of this that I feel is going to be relevant, which basically means when you read through these, underline all number values, okay? It says the yearly interest is $1,405. How much is invested at each rate? Now, here's the deal. When you read through a word problem like this, I say number one here, it says first consider all the given information. How are things related? And do any of these values relate to one another? That's the first thing I want to consider here. So when we talk about $25,000, let's talk about what this is here. It's the total that I invest in two funds, okay? I also know that one fund pays 7%, the other fund pays 4%, and the last piece of information here is that the yearly interest is $1,405. So I will say this, the interest is going to be related to these two interest rates right here. So it's essentially, if I switch colors here, we say the 7% and the 4% are related to this $1,405, and then this $25,000 represents kind of like the total amount being invested. Okay, so that being said, we say, how are things related? We say percentages related to $1,405 interest, and then we could say the $25,000, let's go ahead and write this in, is the total of the amount being invested. Okay, so now, this being said, we say can we write some equations to model this situation algebraically, okay, and what should our variables be? The thing here is this, when you talk about what your variables should be, when you talk about an application problem especially, we always have to start by defining what our variables are. So we're going to go ahead and define them here. I want to make a note of something here. You should always write number of for each quantity here. These have to represent numbers, but we say what should our variables be? You always read near the last sentence, but it'll ask you what you're looking for. So we say how much is invested at each rate? And we say, well, how many rates were there? There were two rates. So we say 7%. So number of really dollars at we'll call it 7% because I reported that first up front. Not that you have to use a particular order here, but we say these are our variables right here. Can we write some equations to model the situation algebraically? The first thing I wanted to do was notice the things that were related to one another. So when I noticed that the 7% and the 4% go with this 1405, what we're trying to do is match up units here. I'm going to be developing a system of two equations and two variables, essentially. And this is going to be true for a little bit here in our unit on systems, but we say two equations, two variables. We'd say 7% is what I will get in interest on the first number of dollars that I invest there, and 4% of what I invest at the other account, I'll get that in interest. So if I wanted to find the total interest, which is 1,405, I'd have to find the interest of each individual account. So we have 0.07 times the number of dollars there plus 0.04 times the number of dollars invested at that amount have to come out to be this total amount of interest. And then our second equation, we would call this like the interest equation. The second equation, this is a zero here, we say is the totals equation. We say we add a totals amount up here. So we say this is just x plus y, because if you add up all the dollars you invest in each account, we should get a total of $25,000. Okay. So what I want to do is find the number of dollars that I invested in each account to satisfy these given constraints to begin with. And so what we're going to do is this, we're going to make a graph of our model using a graphing utility, and we're going to sketch what we see and draw some conclusions from this. So if we go ahead and open up, let's go ahead and do Desmos here. We had two equations. The first one being 0.07x plus 0.04y, so 0.07x plus 0.04y equaled, I think, $1,405 in interest, and I can always fix that. And we say x plus y equals $25,000. Now, when we make a graph of this, you gotta consider something here. These are both in standard form, these equations of these lines. So like this second equation here, x plus y equals 25,000, it has y-intercepts and x-intercepts of like 25,000. So we're going to have to go from like, let's say negative 10 on our x out to at least 25,000. We'll go up to 25 exactly, 25,000, and we'll go by steps of like 5,000. And then on the y-axis, we'll do the same thing. We say y-axis would go from negative 10 out to 25,000, and we'll go by 5,000s as well. And what I want to do is I want to grapple these, because what I want us to realize is as we look at this problem right here, we're saying when I graph the line x plus y equals 25,000, which by the way is this it's this blue line right here, what we're really saying is this is the set of xy points that when you plug them back into the equation make them true. Okay, make this statement a true statement. And so we say this top equation represents all the solutions to the interest equation. What we want to do is we want to satisfy both simultaneously. So we say what point on their graph would be significant here, and I would say it would have to be this point that they both have in their solution sets. So we say 13,500, comma 11,500. So we say sketch what we see, what conclusions can we draw? Well, essentially, you know, we said from a graphing utility we had something look like this, but when we draw on this point right here, we have 13,500. Don't put a comma in there. We say 11,500. You see why I don't want to put a comma, is because this right here. But we say what this represents is some amount of dollars I invested in each account. Okay, and we say the cool thing about this is if we were to plug this back into either equation, we would get a satisfied statement. So basically, we're looking for the solution that they have in common when you solve a system. Okay, so it says use the table feature on our graphing utility to view the values for the graphs. How do these tables relate to the graphs that you constructed above? Okay, so really quickly, let's take a look at this table of values here. We can actually, we can fold one out for both of these equations. As a matter of fact, I thought we could. Possibly not. Let's click on this here. Nope. Okay, well, we're not going to make a table of values here for this one. But we could see that the table of values would reflect all of the solution pairs we're getting in both graphs, okay? So when we say now that we've considered everything, what can be said about our initial question, how much should be invested at each rate? The thing is we want to take this solution pair and we want to make a conclusion statement. And so in the first case we said, you know, these both represented a number of dollars and we have a certain number in each account. So we say invested at 7%, and I'll use not complete sentences here, but we say at 4%. But this is the conclusion that we've drawn right here, okay? So when we solve a system, what I can tell you is this. The best practices are to just identify any important numerical amounts, talk about how they're related to one another, and form some equations using those after you've defined your variables, okay? We can also say this, the solution is always the point of intersection of two graphs, okay? When you talk about the solution of a system, point of intersection, and we can actually plug this back into both to see it satisfies both of these equations. Okay, so really quickly before we move out of this video, it says what general statement can be made about the graph of a system and the solutions to the system, and where do solutions of the system exist on the graph? So we say solutions. Basically, we want to transplant this statement right here. Solutions that occur at point of intersections of the equations in the system. Okay, and I asked this question: can we think of any instances where systems may have more than one solution or no solutions, and sketch any examples to support our claims? Well, when we talk about solutions occur at points of intersection of the equations of a system, then really we could say, well, what if I wanted more than one solution? Can I think of two functions that would run into each other more than once? And I would say, how about a line and a cubic? This would have a solution here, this would have a solution here, and have a solution here. Whereas if I were to say two things that never have a common solution, I could say, well, what about a parabola and a line? You know, these two graphs would never have a common solution. So we would say no solutions. And, you know, we could say here we have three solutions in particular, but we could say multiple. This would just be a representation. And you could come up with your own representations. But this is what we talk about when you say solving a system. More than one equation, more than one variable.